Well, you're sitting down, so I'm going to sit down too. I had come here before. I used to come here. They had comfortable seats. And over at KU at the Med Center in the library, you just had to sort of squat down in the middle between the shelves. And so if you wanted to read a journal, which I always like to do, somebody told me about this place, and I walked in, and nobody told me to go away. So I started coming here to sort of relax. And we also go to the, while I was working at KU, I was working with a European guy from Italy, and he felt like it was very important every day for lunch to go out. You shouldn't eat out of a bag in the lab. And so we went down to the plaza, and I would always be close by, so I had to drop over here. And I could tell everybody when I got back I'd been to the library. When Eric wanted me to talk, I think there's one thing on the net where I talked very briefly about the 17th century and the development of, that's when science actually got cranking. It was in the 17th century in England, and our science as we know it today. I'm not really a historian. I can't remember all their names. There's a whole lot of people involved in this. I'm going to talk a little bit about that. I'm going to sort of set that up by talking about what is really science? What were they doing in the 17th century that is now considered to be the birth of modern science? And it's usually the modern empirical science, which is the kind of science we do, which is like very different from the sort of science that people prior to the 17th century did. Most people that did science, they sort of had there were people like Rene Descartes, for instance, he was sort of a scientist, but he indulged himself in a whole lot of activities that these days would not be called experimental empirical science. So first thing I want to do is to sort of explain, or sort of by a story of my own personal nature, about my first approach to empirical science and how, by the time I was a 13-year-old boy in Columbia, South Carolina, and I had come to the realization that frogs had aspirations for space travel just like humans, and that maybe I could help. It was like, by the time I had come to that, I really had already, I was steeped in scientific kind of mechanisms and stuff. I didn't think of it as being anything that needed to have been invented by a whole bunch of people in England in the 17th century. It seemed to me like it was just if you wanted to find something out, the way to find it out was to do something that was related to it and see how that worked. You know, like an experiment is what you would call that. That wasn't something that didn't need to be invented. That until the 17th century, mostly in England, but also in France and some in Germany, the notion that you would do science, that you would go to a laboratory, a place, and you would work sometimes with machines and things that would help you find things out, and that would be applicable to the real problems on Earth. In other words, a laboratory wasn't like a video game. It was really a model of some system that you were interested in finding out about. And I'll get to that later. I want to first tell you about my experience with the frog, sending him into space. So we were like young science to me when I was 13 or 14 meant things that exploded or rockets. And explosions weren't very exciting to me, and so my brother and I launched on a sort of a parallel with Cape Canaveral, making rockets, and we wanted a rocket that would take off slowly like theirs did, and rise majestically, and then go out of sight. And some minutes later, we wanted to see a little red parachute coming back, bringing back the frog. And that was a pretty complex project for 13 or 14-year-old kids. But I knew how, I think they had taught us in probably as far back as the 6th grade because we had a 6th grade teacher that had a little thing called a science kit. And she could get rid of a couple of the more precocious and talkative boys by giving them the science kit and putting them in a special little room. And they had instructions in there about how you would do experiments. And I didn't find it shocking that, yeah, you would do an experiment, like if you wanted to know how to, they had a little bell that you could hook up to a battery and it would ring, and you could do experiments with various switches they had and stuff like that and see how this worked. So I had sort of already gotten used to that. And then when it was in the summer and we wanted to make a rocket, and I said, well, we need some kind of fuel. And we don't want to use one of the fuels that like there was a missile base in Fort Sill, Oklahoma that would send you an amateur rocketry guide. And I realized that you didn't do science by listening to authority. You didn't look up from some big book how to do an experiment. You just did it yourself, and you were the authority because you had done the stuff there. So I did have the book, and I remember there was one page in there where it had a little box down at the bottom. It said, "Never heat a mixture of sugar and potassium perchlorate." It said, just in a little box. It didn't say why not, and it didn't say why you'd want to do it either. But I sort of thought that as a kind of a lead. That was a secret little message from the guy that wrote the book under the austere supervision of his boss. He said, "Don't let the kids do things like that." And so, this was this is in the 60s, 50s actually, so I think about 58, something like that. And drugstores were completely happy to sell you chemicals. If you were the little boy, you came in there and you said, "You got some potassium perchlorate?" And they didn't, at our drugstore, they didn't have it. I said, "What potassium salts do you have?" And the guy comes up with a list. I said, "What about some potassium nitrate?" So we got a couple of little bottles of potassium nitrate. And he didn't ask us what the hell we wanted it for, It was like, these days they would call the FBI quietly. But that was back in the 50s. And we also, people were, if you said that we were making rockets, they thought, good, that we got to make rockets to beat the Russians. So everybody thought you were being quite patriotic if you were making rockets. And even if they were in your neighborhood. So I took the potassium. I said, why am I not supposed to heat this? I wonder. First, I mixed the stuff, and I mixed it in nice, neat little, orderly 10 little piles, different percentages of potassium nitrate and sugar, which I got from my mother, and who was up in the upstairs window, watching over the backyard and hoping that we didn't, or telling us we shouldn't blow our eyes out. That was our only admonishment from her. Don't blow your eyes out. I said, well, as long as we don't blow our eyes out, we're okay. And so I mixed 10 little piles with different ratios of potassium nitrate and sugar. And I did it by volume, although I knew you're supposed to do it by weight. But they were all even little granulated products, and I thought, whatever, it'll work. And so I found out that 6-4 was a good ratio for potassium for the weight. Once I got on a scale, it was 6-4, but it was about 50-50 by volume, which was perfect. You just take a bottle of potassium nitrate, a bottle of sugar, mix them together. And then I tried lighting it without heating it. I just tried to say, what will this do? And it burned, but it burned fairly slowly, but it was wonderful compared to other rocket fuels that I had tried. It didn't have a bad sulfury smell, because it was just sugar and potassium nitrate. So it smelled like burned candy. And then I burned it kind of slow. I thought that will never make a good rocket fuel. So I should try to heat it, which is what the book said don't do. They said not to do it with potassium perchlorate. But so I tried heating it, and once you heated it, sugar, caramelizes when you heat it, and it turns brown, and it starts getting liquid, and it dissolved the potassium nitrate in a sense. So they became a very intimate mixture. Now, if you wait till it cooled and you lit a little piece of that, it would fly all around in the air all by itself. That's a rocket fuel. And so then I had to make a lot of it. And I made a little wooden spoon I could use to stir it. So the bottom of the pot, I had to do this outside, fortunately, because if I had done it inside, I would have made a real mess in the kitchen. Because if you cook it a little bit, you have to put it in a pot and slowly heat it up and stir it. And if it starts to turn dark brown, and these are things I learned by experiments. If it starts to get dark brown, and especially if it gets a little red looking, get out of there. And it'll go up really fast. But if you heat it in a sort of a careful way with a nice, I had a wooden spoon that I had sawed off so it was flat on the bottom, and I could stir it, and it didn't have any mixture, any stuff on the bottom of the pot. So that led to us finally building a little rocket with that stuff, and it worked better than what we had, because what we had was like black powder, or zinc and sulfur. Those were typical rocket fuels for boys, and this stuff worked better because the rocket left the launch pad and slowly went into the air, but it didn't go up really far. And I decided that it was like the problem was, and this is like analytical thinking. This is what I'm trying to get at, is that my thought processes here were kind of things that prior to the 17th century people didn't do. But I was thinking, what's happening in there, and what can you change to make something happen differently? And I wanted it to burn. I wanted it to burn very, fairly slow at first, but I wanted to speed up later. So if Isaac Newton had been confronted with this problem in the 17th century, which he could have been. They had saltpeter and sugar. They didn't have frogs, I guess. But he would have said various geometric kind of arguments. He would have said, well, if you light the whole thing from the middle of the rocket tube instead of from the bottom burning to the top, it takes a certain time to get there. But if you were to drill a hole in the fuel in the rocket, or pour it, the way I could do it, because my fuel was liquid, and while it was setting up in there, I could put a little dowel in there and make a hole all the way. That way it lights on the inside, and it burns to the outside, a short distance, and as it burns, the surface of the ignition of the fuel is getting bigger, because you're taking it's like, you could say, the first derivative of pi over d was like pi, and so it burns faster as it goes on, because it's sort of like you think of if you're lighting something in the center of a ring, and it's like burning out to the edges of the ring, so the ring is getting bigger as it goes. So it would have the perfect effect that just like the Canaveral rockets, that's where you want it to sound, and you want the smoke to be really cool, which it was, and we had to deal with a whole lot of problems. Like, my father got in the way one time when one of our rockets went off course, and it hit him. Fortunately, it wasn't going very fast, but we realized that we had some useless lawn furniture, which we could saw into little sections and glue these little aluminum rings onto the side of the rocket. The rockets got bigger. They were eventually about 4 feet tall, and they were about 1 inch in diameter. But you could glue the rings that we made from the lawn chairs to the side of it, and that could slide over a pole, and so the rocket could have a pole to slide up. And we used like one of these things they put in concrete when it's setting up to keep it from being so brittle. And so we had about a 10-foot long pole there, and it would start. So by the time it got to the top of the pole, it was going fast enough to where the fins could keep the bottom of the rocket down and the front of it pointed up. And then the little rings would fall off because the rocket would start getting hot, and the glue would melt. It was DuPont cement. And so it was a perfect system. And then we had to just put a nose cone on the top. The frog would fit into we had little frogs, and they would fit into a little, they had these little aluminum canisters for 35 millimeter film back then that had a nice little screw cap on the top. And so you could put the frog in just at the very end, screw the thing down, and have a little parachute there, and all that stuff would be up in the very top of the rocket. And the way the fuel worked is it would set up really hard after you poured it. So you'd pour it, you'd make a little hole all the way up through it with a wooden dowel, and then when it got set up, you'd pull the dowel out, then put a little piece of balsa wood on top of that hole, and then pour some more fuel, which would seal the very top of it, because it would stick just like cement once it got really tight. And that would burn away when the rocket was way up, and we didn't see it anymore at that time, but it would slowly burn away, and then we did a lot of experiments to work out the timing, because we wanted it to keep coasting. We didn't want the cone to blow out right away, so we had to put a big chunk of the fuel in there that was sort of a timer that said, okay, the main part of the fuel is burned out. We're going to burn this last bit slowly, and then boom, there's going to be pressure inside here, and that's going to blow the nose cone out. And the frog is in there with some padding. It was a cool system. I mean, I think when I think about it, I said, this was really, we didn't have a systems engineer, but we were little systems engineers. And we had learned this kind of technique from, really, I didn't know at that point where the hell we had learned that. But I had learned that, when I look back on it, I learned that the whole business of scientific experiments, because we did a lot of little experiments to see how it would work. And it seems like that's just natural, that people would have done that. But at any rate, when I started looking into where that came from, and what is it? That was scientists. We were doing science, little boys with no training at all doing science. I had learned it probably from my culture. I mean, science had become a part of the way people thought, or people that do think thought. Everybody doesn't think that way, but like some people thought that way, and it was something that I think we owed, without knowing it, it started, they say it started in the 17th century. I think that's enough about the rocket story. That explains what I'm doing talking about this, for one thing, is that I had learned how to do it. Now, what was going on in England in 1660 when people like Robert Boyle, I knew Robert Boyle's name when I first read about him because he's one of the guys who figured out that if you have a gas inside of a container and like a bicycle tire, and you put more pressure on it, that it will try to get bigger. You would think that everybody would just know that, but like that wasn't the case in England in the 17th century. Boyle had figured out. He figured out a whole lot of things. He's the guy, not Isaac Newton. Isaac came along a little later, but Boyle's the person that said, we got to set up a place where we can do scientific experiments, and not for any. They didn't want to put a frog in space. They just wanted to know about stuff. You know, there were some guys with lots of money in England, in London, in the 1700s that had to do something, and they chose to. In fact, Robert Boyle started this place called the Royal Society. It was the Royal Society of London for the advancement, for the enrichment or the advancement of natural knowledge. That's what they call it. And they started meeting once a week, and there were several reasons why they were doing this and why in the 17th century. And I've read a lot of stuff about this now, and it's real interesting what was going on in the 17th century in England. They were having wars all the time. Everybody was fighting everybody. England was fighting France. England was fighting Holland. France was fighting Holland. France was fighting Spain. There was big battles going on pretty much constantly. And English people were fighting other English people because they were having a civil war in about 1750, 1745, 1750. They overthrew the monarchy there. They had this guy, Charles I, who was the legal king of England. And he was like overthrown by somebody named Cromwell, and they established for about 20 years, they had what they call a Republican form of government, or not the kind we have, but like they called them Republicans for some reason, but they weren't really Republicans. They weren't from the Midwest, and they were actually a little bit fierce, and they cut Charles I's head off. And then they had that kind of government for about 20 years, and then they decided to go back to a royal type, and they got Charles II, who was his son, to come in and be the new king. Well, Charles II was noticeably nervous, you know, because the job history was kind of poor there, and he didn't like the fact that the people were starting to, common people, and on the intelligentsia, we're starting to get into all kinds of discussions in the gin houses. They were drinking a lot of gin, and they also were drinking coffee, and the two of them together get you really nasty, you know. And they would start arguing about things like whether or not you could make a vacuum, because there's this guy, Charles Boyle, who was starting to do that. He had a vacuum pump. It's kind of a fancy backwards bicycle pump that he had, that he could suck the air out of he had a big glass ball that he had made for this purpose, and that was attached. And they have a model of that in one of the rooms around here. I saw a picture of it today. It's not a model, but it's a picture of it. It's a very ancient-looking device, but it was a big glass, like a transparent glass ball, so you could see what was going on inside of it. And that had a top that you could like take off somehow. It was, I don't know if it was screwed on or what, but it was an airtight seal on the top that you could put things in there. And then you could suck the air out with this pump, saying like a vacuum, it was like a bicycle pump backwards, but you could suck the air out of the thing from the bottom. And eventually, and it get harder and harder to do this as the thing got more of a vacuum in it. And Boyle realized that was a vacuum. That's what the Greeks were talking about when they said nature abhors one, and you can't make one. And the church people in England were adamant about the idea that nature abhors a vacuum, therefore you shouldn't make one. And it's like, it's a weird time. I mean, it was just like very strange time to me, because it's not that way now. We talk about other dumb things, but like they had dumb conversations about whether you could make whether you actually could make one. In fact, whether it was a vacuum. And Boyle did things like put a candle in there and then sucked all the air out, and the candle went out. So it's not he says, not necessarily a vacuum, but something's missing that the candle needed. And they didn't know how candles burned at the time. It was sometime later that somebody figured that out, that oxygen, that was Lavoisier or Priestley, I think is the guy that came up with oxygen. They figured out it was the oxygen that was necessary to make the candle burn. Then you put a bird in there, and the bird died. When you pulled the vacuum, says the bird needed something that was no longer in there. And then they started doing all kind of weird experiments, and one of them I'll tell you about in detail, because it's still kind of weird. It's like there was this man who was in Italy called Torricelli, and he had made a thing that he called a barometer, which you could tell what the atmospheric pressure was. And the way you would do this, I had done things like that in the lab myself, because we used to mess around with mercury because we didn't know it was so dangerous. And well, we'd make all kind of lab instruments out of it, and you needed to make a thing that would tell you what the pressure was inside of the distillation that you were running. And so you'd take a long tube, and you'd fill it full of mercury with a little funnel, and it'd be like a tube about that big around and about like 4 feet long. And you'd take a torch, like a propane torch, and run it up and down the tube, sort of boiling the mercury, giving yourself a good dose of mercury vapor. And it would like all the air bubbles would go out of the mercury that way, because you didn't want it to have air bubbles in it. And then the way we would do it was one end of the tube would be sealed, like it would be closed, and the other tube would be open, and on the open tube, we'd fill the whole thing up with mercury, and then you take a fat rubber band and put it over the top. Now, I don't think they had rubber bands in the 17th century, although they may have. They might have had pieces of rubber. I've never seen one described in any of the books that Boyle wrote about this, but he didn't say what I think they probably used their finger. We knew not to put our finger on it, because your finger would get dark colored. But we weren't afraid of mercury, because we had been introduced to mercury by our mother. Like, give us thermometers and we would break them. And the mercury, we put it out, and it was fun to see the little balls of mercury on the floor. And so we figured mercury was all right. But you put a rubber band around the thing and then drop it into a bowl full of mercury. Okay, so you take the open end and put it with this rubber band holding the column of mercury up, and then you pull the rubber band away. And once the tube is in the bowl, the mercury won't come, some of the mercury drops down. The level doesn't stay quite the whole tube. It drops down to 760 millimeters is what it does, and we know this today, but they didn't understand this. The air is pushing on the mercury that's in the little bowl with the pressure of the atmosphere. And everywhere else except in this tube, there is the pressure of the atmosphere. And the mercury starts falling in the tube, and it leaves a little vacuum where between the closed end of the tube and where the mercury stops going down at 760 millimeters from the top of the little puddle. I mean, the little bowl full of mercury. And they didn't understand that. But they were fascinated by the Torricellian space. That was the little space between the top of the mercury column and the closed end of the tube, which was up in the air. There's a little space in there. What's in it? There can't be any air in there, because it used to be full of mercury until you flipped it over. You didn't let any air in from the bottom. So there was a space there between the top of the thing and 760 millimeters, which they didn't notice. Boyle didn't notice. It's always 760 millimeters from the little bowl. And it's caused, he knew it was caused by the pressure of the air, but he didn't, none of the places I've seen him writing, but did he say it's exactly 760. But they were fascinated by that space because it was a vacuum, obviously. It had, unless it was mercury vapor, which they had no idea that there would be such a thing as mercury vapor because they didn't know what mercury was. They didn't realize, in fact, this was in the 17th century, they didn't understand that things like air, although there were some people that thought this, that things like air and liquids were made out of tiny little invisible things called molecules. You know, they didn't know that. And they didn't think about, well, mercury can sometimes be a vapor. It's not always like a liquid. But it was pretty much a vacuum up there. And they said, that's a vacuum. Well, that was a real mystery around Europe. That was Torricelli was Italian. The idea of doing that experiment inside of a chamber which you could suck all the air out of, meant you had a handle on what caused that in the first place, what caused the mercury to stay up in the column. You know, because what happened if you put this if they put this whole apparatus into their vacuum chamber and then pull the vacuum on it, the column would drop because the air that was pushing the mercury up into the tube, and they had a hard time getting their arms around this idea. A lot of you probably do too. But the mercury was going up in the tube because the mercury in the bowl was being pressed down into the bowl and into any place that it could go by the pressure of the atmosphere. And once they sucked all that out of the chamber, then the little mercury level came down. And it should have, if they made a perfect vacuum, it should have come down right to the edge of the mercury in the bowl, which it never did, because they didn't never make an absolutely perfect vacuum. And they had lots of little philosophical discussions about what's happening here. And why is it only, you know, the mercury level would come up and down at the bottom. As the vacuum came, they would suck on the thing some more and it would come down a little. And there must have been somebody there that said it's not only on the bottom because the vacuum is not perfect. I mean, they were talking about the fact that the air was leaking back in there. They didn't really put their finger on what was going on exactly, and that it was exactly 760 millimeters above or close, varying depending on how much vacuum, above the little bowl. They milked this experiment to death. I mean, they did a lot of things in that vacuum pump, and they would always, for weeks and weeks after, there would be treatises back and forth in London between various people saying this is what's happening there, other people saying this is what's happening. And there was the biggest group of people that were arguing were led by this guy named Thomas Hobbes, who was a philosopher who did not like this nonsense down at the Royal Society meetings at all, because it was in his mind that if you wanted to know something, like a deep philosophical truth, like is there such a thing as a vacuum, for instance, the way to find out would be to find the biggest, oldest book and read that book. That was where the answer would be. And there was no sense in messing around in a laboratory setting. You know, it wasn't really the real world, for one thing. He was worried about, is there a vacuum in the real world? And what would it tell you that it was in a... The idea of doing scientific experiments like that in a laboratory situation had not really caught on. It had caught on with people like Boyle, and it finally caught on with Newton. There were a whole bunch of people whose names I can't remember that were all involved in this. They would meet every week, and they would do the experiments. Anybody that wanted to could do an experiment. It wasn't just Boyle, but you could bring in an experiment and you could show it, because it was thought that if you did an experiment by yourself, which is what the alchemists did. The alchemists they were doing chemistry at this point, but they didn't do it in public. It was all secretive, because they were thinking they were going to get rich, because they were going to make gold, and they didn't want to tell somebody exactly how to do it. But they were just very secretive in general. And this idea of doing it in public, Boyle said, if you want to do, what we want is matters of fact. That's what they're trying to produce, matters of fact. They weren't trying to make gold. They weren't trying to make anything. They didn't have grants from the government that said do this and do that, because they just had money their own and time on their hands. And they wanted to produce matters of fact, which would be in competition, really, with the philosophers, who all had a system of the world that they had written a book about. Books were starting to be used by the 17th century, and so you could print books, and maybe 6,000 copies, which was a lot for the time, but they would sell sometimes. I mean, some Boyle wrote a book that published and sold 6,000 copies. It was ridiculous, and that people would buy it because they were very boring. And but they were talking about this was kind of, to them at the time, this is the way we look at the Large Hadron Collider, say in Geneva, in Switzerland, the border between Switzerland and France, where we're looking for the Higgs particle, which a lot of people think somehow this is going to tell us a lot of special things. It's not. I mean, who cares? I mean, most of you probably never heard of it, or you heard of it, and you say, what the hell is that? I mean, and that's exactly the right attitude, because, in fact, the Higgs particle is a theoretical kind of a thing. There's a lot of money going on in this thing. And it's just as important as what was going on in the Torricelli space, and just as ridiculous with regard to their lives. I mean, the people in the 17th century were much more concerned about, like, whether or not you should go to church, or whether or not the head of the church in England was more important than the present ruler. That was the kind of issues that really stirred the people. This was going on in a tiny little group of people that were going to start what they called the scientific revolution, but it really wasn't relevant at all to what these people. Plus, this is something I got into once I started looking at the 17th century. The temperature was about 4 degrees below average for about 80 years in the 17th century. They call it, geologists call it the Little Ice Age. And there was no good reason for it, because they weren't doing anything to their atmosphere, right? Why has God made it cold? But it got cold, like in about 1620, it got cold, and it didn't really warm up until maybe 1710, something like that. It was meaning that in the wintertime, the Thames would freeze. Now, they weren't used to that. The people in London were not used to having the Thames frozen over for 2 months, but it would do that. But instead of putting up big signs and saying, stop polluting the atmosphere or whatever, you're doing something wrong here, stop those dumb experiments down at the Royal Society, they just went ice skating. They set up little winter fairs out on the Thames, the frozen Thames, and sold things. It was cold. They made a lot of inventions during that century that had to do with, like, how to keep your carriage warm when you carry part of your coals from your fire in the carriage. They had little things that fit under tables. But they hadn't had those before the 17th century. That's how people are sure it did really get cold there, and it lasted for a long time. They had a lot of crop failures all over Europe. In fact, they had crop failures in the United States. That people lived here by then, but mostly the Indians were having trouble with the weather. There was a lot of dying, a lot of plagues, and those are the kind of things that really interested people in London at the time, with the plagues and the hunger. I mean, in 1655, they had a really big plague we call the Black Plague of London, and then there's a 65. I get my dates mixed up because I'm not a historian. And then in 66, they had a huge fire, burned down most of the city, or half of it at least. It was unrecognizable for a long time. They had a bad year there. I mean, a bad bad time during the middle of the 17th century. They weren't interested. Most people did not care anymore. That most people these days don't care about the Higgs boson. I don't either. And I think it's silly to think that there's this one particle that's somehow going to tell us answers to all of our questions. But it's the same exact kind of thing as these people in England were thinking. If we could figure out what's going on in the Torricellian space there, this thing that you can or you can't make a vacuum, if we understand how to do that, somehow it's going to lead us to something else much bigger, which they must have had a sort of a hunch that really was going to happen because they thought of it really important, and it did. I mean, it started, but they did, it started. It came from a different sort of direction. It wasn't that the vacuum pump that Boyle had made was leading the way to something. It just opened up the idea that if you want to find out something, you do it in a laboratory setting, a place where you do a demonstration, you do an experiment, and you do it in front of a lot of people. You can't do it by yourself. I was getting to that point a while ago, and I got lost. I was talking about, because the alchemists always did it by themselves. They did a lot of neat things chemically, but they did them all by themselves, and they were secretive. These guys were starting to do experiments in a public place, because Boyle had made this little pamphlet that said, if you want to discover a matter of fact, you have to publicize it. You have to do it in front of good witnesses. You can't do it just yourself and tell people that you did it. That's not enough. It's kind of like, a courtroom situation now, in the world, where if you want to prove, you bring a bunch of people to listen to you, and you present something, and then you try to convince them, and you all in in the English system there in the 17th century, they would argue about it forever after, and they never got anywhere. If you read their treatises, they just go on and on and on about. Really, they were off the point. They weren't really understanding what it was they were doing, but what they were doing was saying, if you want to do it, I mean, what lasted and what took off in the 18th century and became like the thing that has caused all of us to own something probably on our body right now tonight that kings would have gone to war for in the 17th century. I mean, that's what happened in a mere 300 years, from this notion that if you want to know something, you don't go to the guy with the oldest book. You go to the lab, and you set up something that looks like it, like the question that you want to answer. And it can just be a small part of the question. You can break a question down into a whole bunch of little sub-questions, which all sort of add up. They're all called matters of fact to Boyle. A matter of fact was something that several honest gentlemen, they didn't have any women back then, and they didn't go out at night. And these guys would meet together, and they were all approved people that and they wore good clothes, and they would go to the place that was set. Actually, I was talking about Charles II, and I should have finished that train of thought. But see, it was Charles's nervousness about them having these things outside, like in the gin houses. He said, why don't you do it in some kind of a special place that's safe from drinking, so you don't drink a lot of gin and then do the thing, because then you might get mad, and you might want my head. And so Boyle promised, we will not do any, we will not explore anything in this space which Charles had provided for them. We won't ask any questions that have to do with religion. In other words, God will not, his name will not be brought up in any of our experiments. Now, a lot of people realized they were definitely impinging on a lot of religious kind of doctrines. And Boyle would try to keep it all quiet and under control. But they were talking, I mean, these people they thought the things that these guys were doing their experiments with really had something to do with God. Because, like, say, Hobbes would say, you can figure out all you want to with your little experiments, but really who's running the show here and whose hand is in there, in the place that you say is empty, is God. Because God, by the way, is everywhere, right? He's all over. You can't suck him out of anything. He's going to be in there. And Hobbes wasn't a real God person so much as he said, nature is a spirit. There is no matter that's not alive. And there are spirits inside of that container. When you suck all the air out, you're just taking the air out. You're not really making a vacuum. And that's what the Greeks were talking about. They were saying you can't pull all the spirits out of a container. But it was all translated a few times, and they didn't really understand what they were talking about most of the time in vacuums. Is there any... Oh, that's the clock up there. Okay, because I'm going to go away from... I like the 17th century. I've gotten really enthusiastic about it for lots of reasons. And the one that I was mentioning there briefly was the fact that it got cold, and nobody cared. I mean, nobody made a big stink about it. They didn't, and they certainly didn't think we did anything to cause it. It just got cold. It had actually gotten real warm. When I started reading about this, I went back further and found that there was something called the medieval warm period, which happened in about the 11th century like 1,050 that time, and it lasted for about 300 years. It got really warm, and everybody liked it. It was like crops grew better. Well, in England they liked it. Certain parts of the world they probably didn't particularly like it, but in England it made life a lot better. The only thing it did, which was bad, was it let the Vikings out. And because the Vikings had been surrounded by ice in the wintertime, and they couldn't afford to go on long trips in their boats. But they had these cool boats, and they had nice hats, and they had really vicious kind of clubs. And the Vikings, because of the medieval warm period, the Vikings came out of Scandinavia, went by Scotland, picked up a bunch of women, and took them to Iceland. And this is all documented. I mean, I know about that because if you look at the DNA in people in Iceland now, there's one little part of the DNA called the mitochondrial DNA that comes to you from your mother. So it's only from women that you get mitochondrial, just like your Y chromosome you get from your daddy. But your mitochondrial DNA comes from your mother. And there are lots of people in Iceland that have, they have Scandinavian DNA except for the mitochondria. So they have, the mitochondria are from Scotland. And it's like there's a whole lot of people, most of the people in Iceland actually have that. The people that were born in Iceland have that, and it comes back all the way back there to the medieval warm period. The Vikings got out and they went all the way down into the Mediterranean. They were a nasty bunch of people. And they were my ancestors, actually, on my father's side, because they came up Italy into Switzerland, which is where my father's family was from a little town called Flumes. When they finally came back to North Carolina. But, I mean, one or two of them came back to North Carolina. That's how come I came into the picture. But that happened. The temperature did go up several degrees, what we call centigrade now, and for a long period of time. And nobody did anything to make that happen. It just happened. Now, at the same time, like in the 17th century, when it happened in the 11th century, nobody was really looking at sunspots because people didn't have telescopes. People started looking at sunspots in the 17th century because several people invented the telescope. The first guy to use one was Galileo, and he showed that you can look at all kind of stuff. You can look in dormitory windows. You can look at the sky. You can see that Jupiter has moons, and you can see if you put a smoked glass on there so that you don't burn your eyeball out, you can look at the sun, and you notice that there's spots on the sun. And that they go across, they call sunspots, and they rotate with the rotation of the sun, which is a 27-day thing. Well, those things went away. Like they saw those in like up until like about 1620 in the 17th century, and then they disappeared. There were people by then, like Galileo. There were several other people that were counting them, paying a lot of attention to sunspots. They disappeared. And what people now who are solar astronomers and stuff are saying is those things are an indicator that the sun is really cooking. And the sun cooled down. And sunspots disappeared. The solar constant probably dropped. That's why it got cool in the 17th century. That's why it was warm in the 11th century. It's probably got to do with what's going on right now. But like most people would prefer to blame it on ourselves, which I think is just completely arrogant to think that the little ants here on the planet, have got the ability to change the weather. And it's like, that changed the sun. I mean, the sun was the thing that turned down. The sun went, the power of the sun in the 17th century went down all over the world. They had famines in France, they had famines in Finland, they had famines in the United States, the Indians did. It was a bad time was had by all in this little 17th century thing. And it was warmer back, and nobody knows for sure if it was really, I mean, they know now with tree rings and all kind of little things like ice cores and stuff, they can tell that the temperature did go up in the medieval warm period. The temperature was way up all over the world, and the temperature went down all over the world, and that is the way it works here. It doesn't work on our schedule. And it doesn't care what we do. Whether or not CO2 has anything to do with that, it's a good question. But it certainly wasn't the CO2 that raised the temperature in the medieval warm period. It wasn't some clever Viking thing to make a lot of CO2. It just happened. Nobody knew what was causing it, and nobody right now knows what's causing it, but the sun isn't completely constant, is what the real take-home lesson there is. And the weather, because of that, is not completely constant, and we need to sort of roll with the weather like they did in the 17th century and go ice skating if it gets cold and go surfing if it gets warm. It's like that, and don't worry about it. But that being as it may where it is, let's go back to the scientific method. That's what this talk is supposed to be about. And now what happened in the 17th century, you can tell I don't give this talk very often because I don't know where I'm going. But like, I'm just sort of going around and things that, I mean, I like the 17th century. I hope you can get that. I just think it's a fascinating time. But a lot of things were sort of happening there. And the idea that the scientific method, which we now call it, was actually being established in a weird way. Because they didn't really know what they were doing, but they were establishing the scientific method. And they were talking about all kinds of like social problems and religious problems and stuff like that. And the scientific guys, these people in the Royal Society, they were trying to stay within the realm of what would not get them arrested, basically. Because I mean, if they started any fights there about the issues that they were exploring, they would have been shut down by Charles. He said, but that's not what I had in mind. I was hoping you guys were going to be calm. And so they had to, all through their writings and stuff in that period, they were calm. But then they escaped from the 17th century. I mean, the concept did. And like Isaac Newton came along with mathematics added to the whole thing, which really was needed. And he was a mathematician and also a physicist. And he's the guy that made the first reflecting telescope, by the way. He made all kinds of things. He was a cool guy. He was a mean person and nobody liked him. But he really knew how to make things and how to figure stuff out. And he said, he's a guy that said, the reason that the moon is going around the earth and the earth is going around the sun is because every mass in the universe attracts every other mass with a force which is proportional, directly proportional to this constant I'm going to call g, and the product of the two masses divided by the square of the distance between them. That's called universal gravitational law. And it wouldn't have gone over too well at the Royal Society. It didn't, because he was a member. In fact, he eventually became the president of the Royal Society. But the concept that an invisible force would connect the moon to the earth and the earth to the sun was anathema to those guys. They said, we do not talk about things that we can't see. And it's like a spirit. Like, what is gravity? I mean, universal gravitation is sort of what, the guys that say the Higgs particle is really the God particle or something like that. It's just completely nonsense. But universal gravitation sort of sounds like you're talking about, to these people particularly, it sounds like, you mean you're talking about a force that's actually invisible and that doesn't have any sort of, it's not heavy, we can't isolate it, we can't find anything. It was thought that if something is going to move something else, for instance, the thing that this was a guy, Descartes had established a theory by then that said the reason that the various things in the sky move is because something's moving them. And something has to keep moving them. And Newton was saying, no, actually, once they start moving, you have to exert a force to stop them. They'll continue to move, if you don't have to have a continuous force. And the way that works with regard to the Earth and the moon, and the Earth and the sun, is the moon goes around the Earth because the moon without gravitation, the moon would be going in a straight line. And Newton said, if motion in a straight line happens by itself, but then the force that was acting on the straight line to tilt, what's happening is the moon is falling to the Earth as well as going around it because of the gravitational field. And that makes it have a circular orbit. It's always a little bit past the Earth before it hits it. It's always falling toward the Earth. It never actually moves out of its orbit. But if you put those things together, like Newton could with gravity being like a bunch of numbers, and he put equations on it, and he said, the moon should move around the Earth with actually an elliptical orbit, and it's connected to the Earth by an invisible force. And the people at the Royal Society would have thought, mm-mm. But then he wrote this cool book called the Principia, and that is actually, I think, considered one of the early tomes that started science, was the Principia Mathematica, which there's 1,000 pages in Newton's scrawly little handwriting. And he had very little letters, very neat, but very little. He was not a very sociable person, but in that book he described almost everything in mathematical terms, which means that not only am I going to say that there's an invisible force, but I'm going to say exactly how much that force draws. And the fact is that's the same force that makes apples fall on the ground, that makes the tides get sucked up in toward the moon. And he did all the calculations because he was a brilliant mathematician. He had to invent a whole bunch of things like integral calculus. He had to invent that. He invented differential calculus. He had to invent that. He had a lot of time on his hands because he didn't have much of a social life. He was completely obsessed by what he was doing, and he had time, and he had a brain that would tell him, how to do mathematics, but nobody else knew how to do that. I mean, there was one guy, there was a man in Germany who was starting to learn the same tricks, but it was very much, science was starting to, it developed out of the mathematization. So he could say, not only does this happen, but here's how it happens, and here's how much force it involves, and here's how I know that it's the same thing from here to the moon as it is between the Earth and the Sun, and the gravity, and Jupiter with its moons that Galileo had seen. All that fit into place. And it said here, the universe out there is really a big machine. And it doesn't have God. God set it into motion, is what Newton said. He made it start, but he didn't mess with it after that. And we can figure out, and we should figure out how it works. That's sort of the Newton thing. But that developed further and further, and by the 19th century, I mean, went right through the 18th century was a time of development of all kinds of useful things. Instead of just a vacuum pump, they made like better guns, and they made drugs. By the 19th century, they were making drugs to take care of the pilots that got shot down by the better guns and stuff. So, I mean, the whole thing had really become a massive operation. A lot of people were doing it, and they were doing it and they're making things like steam engine, sort of totally transformed the whole planet. That happened really quickly, and we have sort of forgotten. I mean, I haven't, because I've been reading about this, but a lot of people have sort of forgotten that we are in the same, we haven't really learned all that much. I mean, Newton said, here's how it works, but in the end, he said, it works because there's this force that we have no idea about it. We don't know what that is. The gravity, what is it? I can put numbers on it, but I don't know what it is. And they thought is meant, get some of it in your hand. Show me what it is. Put it in a bottle. And he couldn't do that with it, and he was disturbed by that, as a matter of fact. He didn't like the idea of force at a distance. They knew if you hit something with a stick, it should move. But if you just push something towards something, like if you have something that's charged negatively and you push it towards something else that's charged negatively, that's another one of those mysterious things. They said, what is that? We don't accept that because we can't see a connection between the two things. And there ought to be a connection. Otherwise, it's force at a distance, which is, in fact, something that magicians talk about, but that scientists don't talk about. So they had a hard time with that in the 17th century. In the 19th century, they had gotten used to the idea because they just got used to magnetism, electrical things, and forces. And we are very into forces at a distance now. It doesn't bother me a bit. Probably doesn't bother you. We have our own mysteries, however. We think, we have these guys called astrophysicists. And their job, as far as I can tell, is to, in fact, I was doing that for a while, and the job was to mystify people. Is to come up with really scary stories about what is the universe all about. And now they've gone so far as to decide that 95% of the mass in the universe is missing. You might have heard of this. And then people say, oh, no, it's not missing, it's just dark. We just don't know what it is, and we can't find it, but it's missing. And And there's also some dark energy out there, which is why the place keeps accelerating in its expansion. There's a lot of craziness in the world. I mean, those things are true probably, and they're fun to read about, but to spend billions of dollars on it is kind of silly. I mean, all there's thousands of physicists that work at the Large Hadron Collider, and they're all not going to be happy until they've got a Higgs boson, and then for some reason, that's not going to end. They're going to come back to work the next day, and they still have to get paid. We could be spending that money for something useful. Like, one of these days, there will be an asteroid that hits the Earth while we're here, while some humans are still here. I mean, it happened 60 million years ago. It blew up it landed near the Gulf of Mexico, off of Yucatan, and it kicked up a wave that would have come through Kansas City at 500 feet high. That's what they say, and they find all of the evidence of that. Most people weren't in Denver that day, and that was 60 million years ago. There's probably nobody in Denver, but there weren't any people, but there are now, and our first view of the next one is going to be on CNN. And they'll say, somebody found an asteroid that seems to be headed right toward where we're going to be in a month. It looks like the thing is heading at us about 30,000 miles per second, which is not fast for things moving in space. And it looks like it might weigh about 300 tons. And when it hits here, it's going to raise, a huge wave. If it lands, hopefully it lands in the ocean. But wherever it lands, it's going to cause a lot of destruction. And we will have really up-to-the-minute coverage right until it lands. But we won't know anything to do about it. We'll be sitting here. If we had taken some of that money that we wasted down there at CERN and at the LHC and put it into, what are we going to do that day when we first discovered this thing? Are we going to send something out there to take it out? Because if you just sent something out there and blew it up, it still come. It would just be in little pieces. So you really need to send something out there to drive it away, like mount a big rocket on the thing and send it off. And if you've got 2 or 3 months, you can think about that. And you can say, well, all we have to do is move it a little bit so it doesn't hit the Earth. But we need to be doing that kind of stuff. It's a perfectly good reason. It's an excuse for having NASA. It's an excuse for all these people that are thinking, we need space tourism and stuff like that. I don't want to go up there. I don't know about you guys. But I'd like to see it. I like to see the pictures, but I don't want to be in one of those little things, that they have going around the place. But I think it'd be nice if we'd pay a little attention to that. Instead, we spent more money on global warming than we spent on protection of the Earth from asteroids. Most people probably don't think too much about that, but it did happen once. It probably happened twice. It's going to happen again. We know there's asteroids out there that we're finding new meteorites all the time. There are some astronomers that are looking for them. They're saying we need to catalog all the Earth-crossing meteors that will become meteorites eventually, and so that we'll know. And any one that's big, we have to pay a lot of attention to. But they haven't found that great big one that has our name on it. The space is kind of empty, and once there's something out there that's in orbit headed toward you, it's just headed toward you. Astronomers could find it and say, here's one. And it looks like it's going to hit the Earth in about 2 months. It would be nice to have a warning and not hear the week before when some amateur astronomer discovers it. But we're not doing that. We're wasting our money on trying to do the same thing those guys in the 17th century were doing, which is quibbling over some little space in the tube that said, well, there's a vacuum in there or not. We're doing a lot of that kind of stuff now, I think, with our scientists. And we should say, you guys should be working on things that are kind of have something to do with us. Cure some diseases, for one thing. That would be nice. But worry about, the astronomers and the space people ought to get on this business of what are we going to do in the case that there is an asteroid headed toward the Earth. So now I started this with my little rockets and tried to talk about the 17th century. I know it's very muddy, in there. But, you know, I'm not a history professor. I remembered all the things exactly in the order that they happened. But I think I presented a little flavor of that. And I think they were, by the 18th century, they were a little bit more advanced than we are now in terms of their thinking about what was their place on the planet. Who were they? What did they do? I mean, because in the 18th century, they got cranking and they made all these wonderful things that we now have. And now a lot of scientists are still doing that. They're the ones that work for industry. But the whole lot of government scientists are just doing totally ridiculous things, in my opinion. And I guess my opinion doesn't count for much, but I am sitting up here with a microphone. And now I just noticed that it's 8 o'clock. So I'm probably supposed to be, am I supposed to quit talking at 8 o'clock and maybe answer questions? Which I will, and they can be embarrassing if you want them to be, and they can also be about anything.
And I'll have a microphone to come around with any questions. Just raise your hand. Yes, sir.
When did the Islamic culture influenced the science that was discovered because they learned to speak Arabic and be able to decipher Arabic, and the scientific progress they had made in mathematics? Was that an influence to Boyle?
No, it wasn't. That was much. The Arab influence on science, in my opinion, is more as they preserved, and it was, like when we left Rome, it was in a hurry. I mean, and the place was falling apart and burning and stuff. People just scattered all over Europe, and they lost touch with the sort of the classical period, which it didn't really have the kind of science I've been talking about, but it had the kind where it said, you got the biggest book, you're the boss, we listen to you. But it had there were a lot of bright people, you know, like Aristotle. Democritus is the guy who had said, all we got here is atoms and the void, you know, and that was at 300 BC. That kind of stuff had been lost to Europe because when Rome collapsed, it was. But the Arabs came through North Africa, and they went through Alexandria for one thing, and they burned most of the books. They weren't like seeking knowledge; they were just having a good time, and they burned the library. But there were some of the people, there were some scholars that were behind the armies that put out some of the books and saved them, and so it was in Toledo, I think in about 1100 A.D. that meaning the French that came down there and drove the Arabs back a little south. They reclaimed some of our heritage, and there were several other places like that where old documents from Rome and before had been lost. My reading of the whole situation is that the Arabs didn't ever do a lot of their own science, but they learned from the people that they conquered. Like the Syrians were like much more advanced, I think, than the Arabs when the Arabs kind of stormed through there. I mean, the Assyrians, if you look at their history, they had more of a scientific tradition. But I think it was really, science is something that has developed pretty much along with Western civilization. It's not, the Chinese are doing it now, but they're not really good at it. And they might get really good at it because there's nothing wrong with the Chinese. They're a little bit, they don't have as many oddballs as like people like Newton. I mean, science is really done by a small number of people who otherwise would be thought of as crazy. And they manage to support themselves by doing science. But like the really good ones, I'm not talking about average scientists, but the really good scientists are a little bit weird. And so it's a small group of people, and they don't have that many people like that in China, I don't think. I'm just talking off the top of my head, though. But you were asking the questions.
Yes, I loved your story about your beginning science at your 13 and 14-year-old. Do you have a similar type story of how you started thinking of PCR and how that progressed for you in the experimental intellectual
I do,
area?
and I should have mentioned that. That was one of the times when, if I had paid attention to authority, and I had gone back to the books and looked at whether or not, when I first thought of PCR, I was driving my car, and I was trying to save the jobs of the people that worked in my lab at Cetus Corporation in Berkeley. And what had happened to a friend of mine had made a machine that would synthesize DNA by itself. It was like an automated device. And my lab at Cetus was devoted to synthesizing DNA by hand, like little pieces of DNA, not like long molecules of it like it's in a person, but in order to do molecular biology, you need little short pieces. They're like tools. And we made those when we could make them about 3 a month. In our lab, we had 7 people. And then Ron came over with this machine that could make 3 of them in a night. And I realized that my laboratory, I had 7 people. I had to be in a company. I couldn't justify continuing their employment unless I could think of some reason that we needed a lot more what we call oligonucleotides, with little pieces of DNA. And so I started thinking of things to do with DNA, with little pieces of DNA. What else could you do with them besides what the molecular biologists were using? And that's where I invented PCR one night. But I was just thinking of various reactions you could run with had oligonucleotides in it and do useful things with it, and I thought of PCR. Now, if I had said, I did go back Monday morning. I was on my way up for the weekend. Monday morning, I went back, and I went to the library, and I asked the guy there, that was back when you didn't have the internet in 1982, and some people had it, but most people didn't have it, and there wasn't a lot of information in there anyhow. So in order to search a library, you had to actually search a library, or they had computer searches then that had like lists of all the papers that had been published, but you couldn't do them yourself. A librarian would do them for you. So I had somebody do that, but I didn't rely on it too heavily because there was nothing in there about PCR, and everybody who was an authority at Cetus that I asked what they thought about it would say, it won't work. I mean, there was several people. Some of them were good friends of mine. And they said, no, here's just something wrong with it. It won't work here. It won't work there. And they didn't understand quite why you'd want to do it anyhow. And I just thought, when I first set eyes on it, when I thought of it, I said, this is going to spread all over the place because it doesn't require any special equipment. It's something that everybody needs to do, which is to amplify DNA. And they'll just do it because it's very simple. It doesn't take a lot of training. And I'll get the Nobel Prize. I thought of that night. My girlfriend told me I was totally off base, and but I did. You know? But see, what I didn't do was listen to the authority. The older guys there at Cetus, who said it won't work. It's not worth wasting your time on. It's pie in the sky kind of, and I just went. Fortunately, in that case, I could do it myself. I could actually do what the people in Boyle's lab did, was they made it. He said, it doesn't matter what they say, I'm going to try it. And once it works, then, you guys go play in your sandbox, But it was that same notion in my head that you don't look to authority if you want to know something new. You go to find out for yourself somehow. So try to keep people in authority from actually having anything to do with your decision. So, okay.
Yeah, I have a question. I'm actually a graduate student here in School of Pharmacy.
Oh, there you are.
And I really loved your quote, you don't do science by listening to authority, and this is definitely going on Facebook.
What's that?
But my question is regarding this quote only. Being a graduate student, and when you start, especially as a graduate student, you have a lot of creative ideas. But till you're a graduate student, till you're a postdoc, you're always under authority. So how do you think one should, harness their creativity so that they can be, if not a potential Nobel Prize winner, but maybe do something,
I sympathize with that problem. I have been lucky in my life in that the people who were my bosses were either not terribly interested in me, or they were, and they knew, they just, like I had a really great professor when I was a graduate student. I was at Berkeley, and I stayed there for 7 years because I liked it so much. But he just let you do anything you wanted to. He wasn't interested in you doing something in his field so he could publish a paper. His job was to teach you how to do biochemistry and to make sure that if you needed any equipment or any supplies or anything, that stuff would be provided. That's what his idea was. Most professors are interested in their own career. They want you to do something quick that will get a publication, which will help them get a promotion. That's what they're after. And I mean, some of them are nicer about it than others, but that's a common problem in the sciences. And the solution is not some fixed thing, or people would have discovered it. But it's, you know, I managed to find a place to do what I was doing always. I've always been this way. I've found a way to not have an authority telling me what to do. And that's not easy. I mean, it meant going to work for a company instead of going to academia. Because in a company, you could find a little niche like I did, where I say, I can make oligonucleotides here and nobody cares. And eventually they didn't care whether there wasn't somebody watching me all the time saying, make sure this week you do this and next week you do that. So I sympathize with the problem you're talking about. And the solution is you have to use a little bit of your own kind of, I'd say, skills in manipulating other people, or finding yourself a place where there is somebody who appreciates you and says, okay, like at CETUS they said, 10% of your time you can do what you want to do. You expect it to be at work, but you can do your own stuff. And that to me meant 90% of your time you can do that, because nobody's really counting hours and watching. So I sort of stayed out of the fray. I didn't say, I'm going to do my own thing and I'm not going to listen to any of you people. I just kept my mouth shut and just did it. So there's ways around the system that if you really have an idea that you want to pursue, you should be able to do it. But you sometimes have to sort of make a place to do that in.
Dr. Mullis, we have a question over here, and due to the time, and Dr. Mullis has another commitment after this lecture, this will be the last question.
I didn't know that.
Thank you. Dr. Mullis, I think we were all intrigued with your early days. You gave no real credit to your parents other than maybe toleration. You gave some small credit to a possible teacher of science at school. Mm-hmm. My question is, other than your own innate curiosity, is the educational system today preparing people to think along the lines that you think science needs to be evaluated on?
I would say not so much so that I'm not having I don't see it a lot. But there's, like I'm saying, for somebody who really wants to do their own sort of stuff, there's ways to do that, I think, without really upsetting too many apple carts. As far as the various people around me when I was young, I mean, I had one really good, I didn't mention Dr. Parks, that was a little later, actually. That was when I was almost to graduate from high school. He said, if you want to know something, you know how to find out. I don't know everything, but when you ask questions, go to this book or go to this, or you know how to use the library, basically. Just do that. He was the first person to tell me, he says, you're responsible pretty much for your own knowledge. You're not going to always have somebody to look up to and ask how to do it. And my mother did have the various, her function there was to keep us alive. And she didn't interfere too much, because there was always, for those things that we did that were looking a little suspicious, there was always behind the garage. There was a space back there that we could really do the scary things. But so she didn't interfere with us, but she gave us, she was supportive in the sense that she didn't stop us. I kept, anhydrous hydrazine in the refrigerator, right? And so she didn't have anything against that. What's that? Oh, Nancy wants me to tell you. My mother did have a really nice trait. She had 4 boys, and we had a lot of closets, like we call them storage rooms in the house. They were like, little rooms inside of the house. There were big closets, and she assigned us each to one of them. I had a little place that was big enough for me to have a desk and some storage area, and it was a pretty big space. It was about like this. It was an old house in South Carolina. And so each one of us had those, and that was our private place. We could lock that door. And I had a lock on my door that involved a magnet and a nail so that I could open the door from outside. But it was your little place to do what you wanted to do. And Nancy thinks, and I think that was important too, to give your kids some kind of a private space that they can do whatever they want to in there.
Thank you, Dr. Mullis.
Okay. Okay.
And thank you for attending tonight's lecture. Remember, this Thursday night, 7 p.m., Nuclear Safety, America's Approach. And then our second lecture in the Nobel Laureate Series is a week from today with Martin Chalfie and non-translational research. And I also want to point out, Dr. Mullis mentioned Boyle's air pump. There's the image of the air pump. It's in the exhibition case, the first case you come to in the West Exhibition Gallery. Thank you and good night.
Well, I know that wandered. That was great. Wandered all over.